Hello everyone and welcome to this video. Today we want to talk about electric charge and current. And before we do that though, real quick, I want to make sure that we understood the main concepts from the previous videos. So I'm just going to real quick demonstrate what I was talking about earlier. So in this course, the assumptions that we're making is that the rate of change of the magnetic flux is equal to 0 for all our devices that we'll be working with, for all the lumped devices that we're going to work with. And that's one assumption. Then the other one is that there's going to be no charges, electric charges, being stored in any of the devices that we're talking about. And that is, what that means is there's going to be no net electric charge stored. So if you have something going into the device, some current going into the device, it must be coming out of that device. The current in is equal to current out. So that's another thing here. But you might be wondering, well, what about a capacitor then? Doesn't a capacitor store charge? Yes, it does, but the thing is, when you have a capacitor here, you're going to have positive charges on one side and negative charges on the other side, producing an electric field from the positive to the negative, just to stick to the conventions. But the issue here is that if you look at this whole thing here, you're going to have a net charge of 0 though. So for every positive charge, approximately, there's going to be a negative charge, which if you take a closed surface around that, there's going to be no net electric field lines coming out of that surface. So for this element in its kind of black box or blob shape, there's no net electric flux coming out, at least in the idealized assumptions that we're making here. And the other issue here was that the other assumption was that, so that's the first one. That's the second one. So the second one we just talked about, there's no net charge being stored on any device that we're going to talk about. Resistors don't store any net charge. Capacitors don't have any net charge. They have the same charge stored on both sides that we just talked about. So the other thing here is, the first one is, so we talked about that. If you look at some closed loop, so we have a circuit here, and it's got a power supply, plus, minus volts. We have some basic circuit here. The idea is that the magnetic flux inside of this guy is not going to be changing at all. So meaning there's going to be no induced voltages or electromotive forces inside of this loop. Well, what does that mean? In other words, you basically are not going to be working with circuits in this class where you have some kind of a device like an inductor or transformer or anything like that that is constantly changing in magnetic flux and is changing the magnetic flux of this circuit, thereby inducing voltages into here. So another scenario would be, we cannot, to kind of make a silly example here, we could not analyze these circuits if we had a bar magnet, and his was the north side and the south side. We could not analyze this circuit with the equations that we're going to be working with if we brought this magnet in and out of this loop that we have here. And I want you to think about the reason. Why is that? Why is it that we cannot be certain of our measurements, of the voltage and current measurements in this circuit, if we were to bring some magnet in and out here at some rate of change of the flux? Well, the reason would be, as I just mentioned, the flux, we cannot change that flux, because if we do, this loop is going to, for example, let's say that we're going to bring this magnet into the loop. What's going to happen is there's going to be a net increasing magnetic flux in this direction. So the circuit is going to, the loop is going to resist the change in magnetic flux, and it's going to make it produce its own flux to keep it the same. And what's going to happen is, well, how do you produce such a magnetic flux where it's going to oppose the change in magnetic flux? Well, if you have a And let me draw this a little better so it's not confusing. So let me draw it at an angle maybe. So suppose we have, I'm trying to draw this at an angle so you can see it better. So we have that resistor here, rectangle shape here. Then you have this magnet. You just draw a bit white here. You have that magnet, and let's show where it's coming out. Remember, it's going to come from the north side and go to the south side. If we bring this guy into here, what's going to happen is you're going to have a net increasing magnetic flux, because as you can imagine, more and more lines here are going to be coming into, you're basically increasing the magnetic flux of this loop. And what's going to happen is that the loop likes it so that the magnetic flux doesn't change, so it's going to produce its own magnetic flux this way to oppose the change. And you got to think about what kind of because we know currents produce magnetic fields, in what direction does the current have to go to produce a magnetic field going this way? Well, we use the right hand rule, and we see that if you wrap our fingers in this direction and have our thumb go this way, that's the way the current has to go to produce that magnetic field to oppose the change. Thereby, we're going to have, if you keep bringing this in and out, we're going to have currents going back and forth and energy being induced into the system. So then this is not going to be, you're not going to be able to determine the currents and voltages across this resistor, because they're going to be increasing and decreasing. So those are the two main ideas here. So now let's just dive into electric charge and electric current then. What is electric charge? That is the most fundamental electrical property that we're going to be talking about. Electric charge is just like, or not just like, it's similar to a property of objects called mass. When I have some atom here, it's going to have, well, we know it's going to have some mass, because when you compile all these atoms together, you get, for example, an object or a human being or anything like that. So therefore, they must have mass individually, and when summed up together, the mass increases. So if you look at this property of charge then, which is represented in coulombs, what it's going to be is a certain property, electrical property, that all protons and all electrons have. So let's call this a proton, a positive charge, and an electron, a negative charge. And now remember that the masses are different. The mass of the electron is almost negligible. It's very small. But the mass of the proton is about, I believe, about 1,000 times bigger than that of the electron. So the masses are much different, but the charges are exactly the same. We'll call that E, the elementary charge. And the only difference is that they're exactly opposite. Meaning the charge of the electron is negative and the charge of the proton is positive. So now the difference in the positive and negative is a matter of mathematical reasoning, so we'll be able to do add them and subtract them. But you could have, do notice though, you could have just called this guy positive and called this guy negative. It's literally a matter of distinguishing between two objects being the opposite of each other. Just like a vector, when I say I'm going this way, well, what is the opposite of that vector? The negative v is the exact opposite direction. Now, this vector could have been going in this direction to begin with, but this negative of that vector is just negating its identity, meaning whatever this guy is, that guy is the opposite of that. Now, that could be in a directional sense, or in a sense of opposite charges, as we can see here. Well, we know there's no negative mass, so that doesn't really make sense in terms of mass. But in the domain of charges, it does make sense, because charges come in two varieties, positive and negative, as we talked about just now. So this coulomb, though, is defined in terms of current, but we'll look at the simpler definition for now, which is that one electron has the magnitude of the charge of one electron is equal to 1.602 times 10 to the negative 19 coulombs. You can see that it's a very small charge, but then do realize though that 1 coulomb is a huge number. And to find that, let's see, I'll say 1 coulomb divided by 1.602 times 10 to the negative 19 coulombs per electron And what's going to happen here? What I'm going to get is, what's going to happen is I'm going to flip these guys, and flip the units, and the coulombs cancel out, and I'll get electron on top. So if I divide that out, I'll get something in the order of 6.24 times 10 to the 18 electrons. That's about 1,000,000 times bigger than 6.24 trillion. So you can see that it's a very, it's like a 1,000,000 trillion electrons, or in that order of magnitude, which is a very huge number. So that tells us that 1 coulomb is a huge amount of charge. And we don't typically see that in nature, because most things tend to be neutral. And the reason being is that for every, this is approximation, but for almost every positive charge you see, there's a negative charge that, even though maybe there might be some net charge, well, it's gonna be negligible compared to the mass of the object and the amount of charges there are in total. For example, if you have the Earth, for example, let's just look at the most extreme case here, the Earth. You're gonna have so many different charges distributed throughout in the oceans and the land and everything, that we can, if we put a loop around it, we can see that there's no net electric fields coming out of, no net electric fields. So I'm gonna cross those out. So macroscopic objects then tend to be neutral objects, because positives and negatives cancel out, and the electromagnetic force is, in this sense, as far as charge goes, is not very long range, as we talked about here. So don't confuse that with electromagnetic radiation, because electromagnetic radiation obviously is very long range, and that's why we can see light from billions of light years away. But anyway, so that is charge then, and I'm hoping that we kind of understood the concept of charge and quantitatively being able to describe them. So one electron then has the magnitude of it is this. One proton has the same charge here, but then the electron has the negative of that. Exact same magnitude as the proton's charge, but the exact opposite charge. So now let's take a look at something else called electric current, which I'll draw some conductor here, conductor surface, and I'll draw some charges, and they're all moving in this direction, for example, perhaps by some electric field being produced here in this direction that is repelling the positive charges in that direction. So if you look at the cross-sectional area here, then we can talk about the amount of charge going through per unit time, and that's going to be coulombs, because charges are measured in coulombs, and that is divided by seconds. So we can then see that if we have a huge number of charges going per every 1 second across the cross-sectional area, we're going to have a bigger current. So that's going to give us something called the current, and as we talked about, coulombs per second, which is the same thing as 1 ampere or 1 amp, which we'll write it short for just one letter A, and that's for amps. And the definition, the formal definition is instantaneous current is the rate of change of charge per unit time. This is instantaneous current. So that's the definition of current, then let's keep that. Now, let's see. Another important point that I should mention about charges before we go on any more here is that, so we know that the charge is some fundamental number for electrons and protons. The other fact that we've observed in experiments is that the only charges that occur in nature are multiples of electric charge E. So you will never find, like, for example, 2.5 or anything like that. It's always integers being multiplied. So I'll put this times n, where n is either 0, 1, 2, and onward. So that's another observation that we had. And the other one is that the law of conservation of charge, meaning charges cannot be created or destroyed, they can only be transferred. So the algebraic sum of the electric charges in a system doesn't change. Only the net electric field lines coming out of that loop, for example, or out of that enclosed system changes, but not the net number of charges in there. So those are some facts to keep in mind, experimental observations to keep in mind. Now that we looked at that, let's take a look at something else real quick, and that is the difference between direct current and alternating current. So if you have a direct current, we're talking about current that is constant. For example, let's say 5 amps with time, meaning as time goes on, it's a DC current remains constant. Whereas if you have a alternating current, which we'll denote as, I really should use the capitalized I here to distinguish between alternating and DC current, so I'll use lowercase I here, and that is going to be some current that is alternating with time, and we'll see the uses of the AC versus DC, the benefits and things like that. Okay, so that's another idea then. And let's see, another big idea is to understand before we go on is the idea that if you have, let me draw a power source here. You have positive, negative volts, and you have some resistor here, some generic circuit. You got to realize that conventional current is a current that's originating from the positive terminal of a voltage source and going in a loop. Remember, current requires a loop to be able to be conducted. So it's going to go from the positive side and go to the negative side and satisfy this loop and go through this loop. So something we need to understand is that the conventional current flows from positive to negative, or high potential to low potential. But in the reality though, we need to know that electrons are actually going from the negative side and they're flowing in this direction, which I will call negative A. Here's what we need to notice, why these are equivalent. If I say I have an I going this way and I have a negative I going this way, that's kind of like the vectors we talked about earlier. It's like negating something twice. I'm saying directionally it's going this way, and this is the opposite in entity of this current here. So what's that going to do? Is kind of like saying I do not want to eat. So then nots cancel out and you say I do want to eat. So the negations here cancel out. And another way to think about it in physical terms is to think about what happens when you have a positive charge here. Now this is a different example now. Some positive charge here, 2 of them for example, and 2 negative charges. If we think about, so right now these are neutral. The net charges in here is 0. But let's now think that I move these positive charges, one of them out. If I move that guy out, what am I going to get? I'm going to get a net negative charge then, am I not? Let me clear this guy out. This guy is cancelled out, the positive and negative. The net charge in this surface is 0, but then here now I have a negative 1 here, so I have a negative 1 charge now. How about this though? What if, let's think here, I'm going to do something else. I'm going to put another kind of circular type of thing here, some closed sphere, and I have the 2 positive charges here. What if now I transport 1 proton from here to here? So I'll get rid of this guy and I'll put him right over here. So what happened is that the net charge was +2 initially, and the net charge here was -2 initially. What happened then was that I transported 1 guy out, so then I got +1, and over here these guys cancel out, so I got a -1 here. But wouldn't I get the same exact thing if, instead of doing all of that, Let me put this guy back where he was. The idea I'm trying to demonstrate to you is the fact that if you get a positive charge here, that is the same thing as bringing a negative charge from here to here. And let's demonstrate that then. In theoretical terms, if I now take a negative charge, put him into here, this guy's going to be gone. So now what I'll have is a -1 charge here, net charge of -1, and these guys cancel out and get a net charge of +1. So we see that in either case, we got the same thing here. Initially, we had that -1 here and a +1 here, and what that tells you is that a positive current flowing from here to here, let's call that I, is the same thing as a negative current flowing from here to here. And that kind of makes sense if you think about it. When you have, let's think about somebody's house, your house for example. You have your house here, and if we treat heat as an entity and cold as an entity, so let's say the outside world is cold. Remember now, cold doesn't really exist. It's only the lack of heat. And just like darkness doesn't exist, it's the lack of electromagnetic rays or light. But if we're going to treat the cold as a mathematical object, as a positive or a negative, to be able to do some math with it. So let's see, if I treat that as a, let's say, let's call this, we have 3 units of cold outside, if that makes any sense. Let's just call it that for quantitative purposes. So we have 1, 2, and 3 here. And let's say we have, like, for example, 4 units of heat in here. We're just kind of quantizing energy here. So let's say now if I take one of these guys out, the heat out here. So what happened there is, I'm going to lose 1 unit of heat in the house, and I'll be left with 3. But then, isn't that the same thing as me opening the door and having 1 unit of cold come in and cancel that guy out? So here's another example, kind of intuitive one, with the heat and coldness, that when you have heat leaving, that's the same thing as cold entering. So that's the same kind of idea here. Even though positive charges don't really move for circuits, it's the electrons that are moving back and forth. We can see that electrons going from here to here is the same as protons going from here to here. So that's why we use conventional current. It avoids a bunch of negative signs in our Ohm's law and other equations, and it's kind of a convention that's stuck, and it's kind of easier to do the math with it. I think I'm kind of overdue on time, so I'll see you guys in the next video. Thank you for watching.